DSPy employs a declarative programming model where task behavior is specified through signatures, enabling the framework to optimize prompts and model weights automatically. This artifact demonstrates the use of the BootstrapFinetune optimizer to refine a classification module by distilling prompt-based reasoning into fine-tuned model weights. We will examine how the classification signature is defined with input fields and constrained output types, how the ChainOfThought module is initialized with this signature, and how the optimizer compiles the module using a training set to produce an optimized version capable of accurate label prediction.
Import DSPy. LM equals DSPy. LM OpenAI /GPT-4 Omni 2024-07-18. Hash define the DSPy module for classification. It will use the hint at training time, if available. Signature equals DSPy. Signature text, hint label. With updated fields label. Type equals literal tuple classes. Classify equals DSPy. ChainOfThought signature. Classify, set LMLM. Hash optimize via BootstrapFinetune. Optimizer equals DSPy. BootstrapFinetune metric equals lambda x, y, trace equals none. X label equals y label, num threads equals 24. Optimized equals optimizer. Compile classify, train set equals train set. Optimized text equals, what does a pending cache withdrawal mean? Hash for a complete fine-tuning tutorial, see https DSPy AI tutorials classification fine-tuning.
This code demonstrates fine-tuning a DSPy classification program using BootstrapFinetune, an optimizer that distills prompt-based programs into weight updates for the underlying language model. The approach begins by defining a classification signature with input fields, text, and hint, and an output field, label, constrained to a predefined set of classes. A ChainOfThought module is instantiated with this signature, which enables the model to generate reasoning steps before producing the final classification label. The optimization process uses BootstrapFinetune with a simple accuracy metric that compares predicted labels against ground truth. The optimizer compiles the classification module using a training set, transforming the original prompt-based program into one where each step is executed by a fine-tuned model. This is particularly useful when you need an efficient program after initially developing with a larger LM, as it distills the knowledge into a smaller, fine-tuned model while maintaining the same program structure. The key advantage here is the ability to leverage the reasoning capabilities of ChainOfThought prompting during development, while ultimately deploying a more efficient fine-tuned model. The trade-off is the computational cost of fine-tuning, though the example shows significant accuracy improvements from 66% to 87% in the informal run mentioned. This pattern is ideal when you've validated your approach with a larger model and want to optimize for inference efficiency without sacrificing performance. Let's break it down.
Import DSPy.
Imports the DSPy framework for programming with language models, providing tools to define, optimize, and execute LM-powered modules.
LM equals DSPy. LM OpenAI /GPT-4 Omni 2024-07-18.
Creates a language model instance using DSPy's LM class, configured with the OpenAI model, GPT-4 Omni 2024-07-18 as the backend. The variable LM now holds this language model object, which can be used for text generation tasks within the DSPy framework.
Hash define the DSPy module for classification. It will use the hint at training time, if available. Signature equals DSPy. Signature text, hint label. With updated fields label. Type equals literal tuple classes.
Creates a DSPy signature for a classification task that takes text and optional hint inputs, and outputs a label. The signature is constrained so that the label field must be one of the predefined classes specified in the CLASSES tuple. This signature will be used to define the behavior of a DSPy module for classification tasks, where the module can leverage hints during training if they are available.
Classify equals DSPy, ChainOfThought signature.
Creates a ChainOfThought module instance named Classify using the provided signature, which will enable multi-step reasoning capabilities for the specified task. The module is initialized with the signature's input-output behavior specification and will use the ChainOfThought prompting technique when invoked.
Classify, set LMLM.
Sets the language model for the Classify module to the specified LM object. This configures the module to use the provided language model for its operations.
Optimizer equals DSPy. BootstrapFinetune metric equals lambda x, y, trace equals none. X label equals y label, num threads equals 24.
Creates a BootstrapFinetune optimizer instance configured with a metric that checks if the predicted label matches the actual label, and sets the number of threads to 24 for parallel processing. The metric is defined as a lambda function that takes 3 parameters x, y, trace, and returns true when x label equals y label.
Optimized equals optimizer. Compile classify, trainset equals trainset.
Calls the optimizer's compile method on the classify module using the provided trainset as training data, returning an optimized version of the module stored in the optimized variable. This process tunes the module's parameters prompts and/or LM weights to improve performance based on the training examples.
Optimized text equals, what does a pending cache withdrawal mean?
Calls the optimized function with a text parameter containing the question, what does a pending cache withdrawal mean? To process or optimize this specific input text. This example showcases DSPy's declarative approach to LM programming, where you define task behavior through signatures and let the framework handle optimization. The workflow starts with a classification signature that specifies input fields and constrained output types, then wraps it in a ChainOfThought module to enable reasoning steps. The key innovation comes from using BootstrapFinetune to distill this prompt-based reasoning into fine-tuned model weights, creating an optimized version that maintains the same program structure, but executes more efficiently. This pattern is particularly valuable when you've validated your approach with a larger model and want to deploy a smaller, fine-tuned version without sacrificing performance. The trade-off is the computational cost of fine-tuning, but as shown, it can yield significant accuracy improvements while preserving the original program's logic.
The ChainOfThought feeds hints to BootstrapFinetune, which kneads them into frozen weights.